So when we talk about functions, really a function is just a specific type of relationship between one quantity and another, such as the letter grade you receive in math class depends on the numerical score, or the amount paid for gas depends on the number of gallons pumped. So when we have a function or a relation, we're going to have two variables, an independent variable, which is the x-coordinate, and a dependent variable, which is the y-coordinate. A relation is basically any set of ordered pairs. So we're going to look at 4 different ways to represent a relation. One is with ordered pairs, like 2, -1. Another is with a table, where we could put 2 in the x column, -1 in the y column. Another is with a graph, where we could go to 2 on the x-coordinate, -1 on the y-coordinate. And the third is a mapping diagram. In a mapping diagram, you're going to have one set of inputs, or x values, and another set of outputs, or y values. And you'll use an arrow to go from the input to the output. So 2, -1 can be represented in that way. So each of these ordered pairs are represented in the table, on the graph, and in a mapping diagram. A function is a relation, but it's a special type of relation in which each element in the domain matches exactly one element in the range. So in other words, each input goes to exactly one output. So here's an example of a function. The input of 2 goes to the output of 5. Input of 4 goes to the output of 5. Input of 8 goes to the output of 12. And input of 0 goes to the output of 4. This up here is not a function because the input of 1 goes to an output of -2 as well as an output of 3. So in terms of ordered pairs, what we're looking for in a function is that we have no x values that repeat. That's how we can tell if we have a function. In the table, we see the same thing. I have 2 inputs of 1, but the input of 1 sometimes gives me a -2 and sometimes gives me a 3. So I can't have any x values repeating in my list of ordered pairs or in my table. These repeating x values of 1, -2, 1, 3 that I see in my ordered pairs are right here in my graph, 1, -2, and 1, 3. So in my graph, what I'm looking for is no 2 dots can be on the same x values. So if I look at this graph, none of these dots are on the same x values. And then in my mapping diagram, here's the problem, is that this input is sending arrows out to 2 different outputs. So in a mapping diagram, you can't have the same number sending out 2 arrows. It's fine for our outputs to repeat, so 2, 5, and 4, 5, that's fine, those can repeat. Do I have that here? Doesn't look like it. Do I have it here? Yes, I have 2 outputs of 2, and that's okay. But I can't have 2 repeated inputs. So let's decide if this is a function. 1, 2, -2, 4, and 3, 4. So is this a function? Yes, it is. It is a function because no x values repeat. It's fine to have 2 y values that are the same. What about this one? This is not a function because the x value of 1 is repeated 3 times. So I have this repeated x value, so it is not a function. Let's look at this one. -4, 1, -2, 1, -2, 0. Oh, I have a repeated x value. So this is not a function. Thinking about domain and range. The domain for a function is the set of all independent variables, or the set of all x values, or the set of all input values. So when we're talking about domain, the domain is x values. Range is the set of all values of the dependent variable, or set of all values of y, or set of all output values. The range is the y values for a function. So if I have a list of ordered pairs, or a mapping diagram, or a table, or a graph of dots, the way that I'm going to give my domain and range is by using what's called roster notation. Roster notation means that I just create a set with those set braces, and I just list all of the values that are in there. So in my ordered pairs, I see that I have 0, -1, 2, and 1. So I list those in here, 0, -1, 2, and 1, but I did put them in order from smallest to largest. In my range, my y values, I have -3, 2, 2, and 0. So I will put -3 first, and then 0, and I have 2 2's, but I only list it one time. So this is called roster notation, and we use roster notation for domain and range if we have ordered pairs, mapping diagrams, tables, or a graph of dots. So let's practice. Give the domain and range of each relation and determine if it's a function. So domain. Remember, domain is going to be the set of all x values. So I've got 3, 4, 4, and 6. Since we're not repeating, it will just be 3, 4, and 6. And I can already tell you that this is not a function because I have a repeated input. So this is not a function. And then for the range, we're going to make a set of numbers that includes all the y values. -1, 2, 5, and 8. And those are already in order. So I just need to list them out. Here is a mapping diagram. Remember, in a mapping diagram, no x value can send out 2 arrows. So 4 is only sending 1, 6 is sending 1, 7 is sending 1, and -3 is sending 1. So this is a function. The domain, I'm just going to use the letter D for domain. The domain is all the x values. In order would be -3, 4, 6, and 7. The range is all the y values. In order, that will be 100, 200, 300. Here's a table of values. In a table of values, I'm looking for any repeated x values. -5, 0, and 5, there are none that are repeated, so this is a function. The domain is the list of the x values in order, which would be -5, 0, and 5. And the range would be the list of all the y values in order, but all of the y values are the same, so it's just going to be that individual number of 2. What about finding domain and range from a graph that's not dots? So here is a graph that is not dots. The domain of a function refers to the set of all possible x values for that function. When the dots are connected, to find the domain, we are going to read the graph from left to right, and we're going to use interval notation to describe the smallest and largest x values that are shown by the graph. To find the range, we are going to read the graph from bottom to top and use interval notation to describe the smallest and largest y values shown by the graph. I think I want to highlight those. Okay, finding domain and range from a graph is pretty important. So here I have domain goes from left to right, range goes bottom to top. The domain refers to all the possible set of all x values. Range refers to the set of all possible y values. So we are going to read this left to right. Understand that all graphs, not all graphs, most graphs have arrows on the ends of them, which means that it continues in that pattern forever. So this graph continues growing that direction. When you run into an arrow first on a graph like this one, if I go left to right, the first thing I'm going to run into is that arrow. That means that graph goes forever in that direction towards infinity. Since it's on the left end, that is negative infinity. So the domain for this graph is going to start at negative infinity. And if I keep scanning to the right, the last thing I run across is also an arrow, so it goes from negative infinity to infinity. Then I'm going to go from bottom to top. When I go from bottom to top of this graph, the first y value that we come across is right here, and that is at -6. The largest y value that I run across is an arrow, which means it is infinity. So -6 to infinity. Since there's an actual dot here at -6, we're going to give that a bracket. So it's going to go from -6 to infinity for this graph. In general, I think I probably wanted this to be somewhere else, but that's okay. It's good to have it in more than one place. In general, the domain of a function is negative infinity to infinity, unless there's a variable in the denominator or inside an even index radical or a logarithm, which we learn about later, like a different chapter. So we'll see this again here in a little bit. Let's find the domain and range for each of these graphs. This graph right here is made up of dots. When it's just made up of dots, our domain and range are going to be in roster notation. So the domain is going to be the set of all x values, and I want to go smallest to biggest. So this first x value I have is -1, and then 0, and then 1, and then 4, and then 5. The range is going to be the set of all y values, and I want again to go from smallest to largest. So I'm going to start at the bottom and work up. So the smallest y value is -3. The next one is -1, and then 1, and then I have 2 that are 2's, but I'm just going to list it a single time. So that would be my range. Now letter B is different because it is connected dots, so I need interval notation. So going from left to right for the domain, going from left to right, the first x value that the graph connects to is -4, and the last one is 4. Since there are actual dots there, I'm going to use closed brackets to include -4 and 4. The range goes from the bottom to the top of the graph. The first y value is -6, and the last y value is 6. So that will be closed bracket from -6 to +6. Letter C, domain. Again, when the dots are connected, we scan left to right. So going left to right, the first thing that I run across is an arrow, which means I'm starting at negative infinity. And the last thing I run across is another arrow, which means I end at positive infinity. So this domain is negative infinity to infinity. And the range, starting from the bottom, the first thing you run into is an arrow. The last thing you run into is also an arrow. So the range is negative infinity to infinity. D, domain. Go from left to right. The first thing you run across on this graph is an arrow, and the last thing you run across is also an arrow. So the domain is negative infinity to infinity. And the range, scanning from bottom to top. Bottom to top, the first y value that we encounter is -3, and the last one we run into is an arrow. So this range is going to go from -3 to infinity. Remember, infinities always get parentheses, and this -3 is going to get a bracket. Okay, because each value of x leads to only one value of y in a function, any vertical line has to intersect the graph at most in one point. This is called the vertical line test. The vertical line test says that if you draw any vertical line, that vertical line can only cross the graph in one spot. Otherwise, the graph is not a function. So we're going to use the vertical line test to decide if these are functions. Well, let's look at these ones up here first. Is this first one a function? Do I have any vertical lines that would run into more than one dot? I don't, so this one's a function. What about B? If I draw a vertical line, that vertical line is going to cross the graph more than one time, so this one's not a function. Letter C, vertical lines only cross the graph one time. This one's a function. And D, vertical lines only cross the graph one time, so this one's a function. Okay, 27. Is it a function? Looking at vertical lines, if I were to draw a whole bunch of vertical lines, none of them would cross the graph more than one time. So this graph is indeed a function. Let's just answer all of those questions first. Number 28, is this a function? Think about drawing vertical lines. None of them cross more than once, so this one is also a function. 29. If I draw a vertical line right here, notice that it crosses through the graph two places. So this one is not a function. 30. Again, if I draw a vertical line, it's going to cross that graph more than one time. So this one is not a function. 31. Vertical lines only cross this graph one time. So this one's a function. And 32. Also, vertical lines only cross this graph one time, so it is a function. Now what about domain and range? Domain, we scan the graph from left to right. On this graph, going left to right, the first thing you run into is an arrow, last thing is an arrow, so domain is negative infinity to infinity. The range, we are going to scan the graph from the bottom to the top. First thing you run across is an arrow, last thing you run across is also an arrow, so the range is negative infinity to infinity. 28, domain. Going left to right, first thing you run into is arrow, last thing you run into is also an arrow, so that is negative infinity to infinity. On the range, when you go from bottom to top, the first thing you hit is an arrow, so it starts at negative infinity. The last y value you run into is this one right here, which is at 4. So the range will go from negative infinity up to 4 with a bracket on 4. 29. Domain, left to right. The first x value we run across is at this point right here, which is 3. So the domain is going to start at 3 with a bracket, and the last x value you run across happens to be on an arrow, so that's 3 to infinity. Range, this one is a little bit tricky. I mean, it looks like it might not keep going, but that arrow tells me it does. So the first thing your pen bumps into going bottom to top is an arrow, and the last thing is also an arrow. So this range is negative infinity to infinity. 30, the domain. The first x value that this graph contains is negative 4 right there, and the last value the last x value this graph has is 4. So the domain will be negative 4 to 4. Range, bottom to top. The first y value you run across is negative 3, and the last one is 3. So that range will be from negative 3 to 3. Whoa, not infinity. Hello. Negative 3 to 3. All right, 31. Scanning left to right. First thing is arrow. Last thing is arrow. So the domain here is negative infinity to infinity. The range. Okay, so the first thing you run across is negative 3, but look at what happens. If I continue this arrow, then I can tell that it should start at negative infinity. And then the last thing you run across is 3, but because of this arrow, it keeps going. So this one's range is negative infinity to infinity. Even though they didn't draw their arrows long enough, it still is. 32, domain. So this one has a dot instead of an arrow. That means the graph actually stops there. So the first and smallest x value that we run across is -2. And then the biggest x value that we run across is +2. So this domain would be from -2 to +2, both including. And the range, bottom to top, the lowest y value is 0 and the highest y value is 4. So this is going to be from 0 to 4. Now when we have equations, we are mostly going to focus on domain in this chapter. Well, not this chapter, this section. In this section, we're mostly going to focus on domain if we have an equation. So, working with an equation to find domain, there are 3 things that we have to look for. This page is going to be super important. You might want to put a little flag on it or something, because we're going to have to come back to domain time and time again. And we have to be able to figure out how to approach, how to figure out the domain. So there's 3 things we've got to watch for. One thing is an even index radical that has variables inside, like a square root or a root with a 4. Then the next thing we're going to watch out for is a denominator that has a variable inside. And the third thing is going to be logarithms with variables inside, but that's not going to come until a later chapter. So the thing we need to know is if it doesn't have one of these 3 things, then the domain is automatically just going to be negative infinity to infinity or all real numbers. So we're just looking for 3 things, and in reality, that's just 2 things right now because we're not doing logarithms until later. So here I have an even index radical. No negativity allowed inside that radical. So what am I going to do if I have an even index radical? Well, what I'm going to do is I'm going to set the radicand greater than or equal to 0. So if you have a radical with variables inside, what are we doing? Setting the radicand greater than or equal to 0. Well, what is a radicand? A radicand is the stuff that's inside the radical. So here's my example. I have y equals the square root of 5x plus 7. The radicand is 5x plus 7. So I take the radicand, 5x plus 7, we set it greater than or equal to 0. We solve that little inequality, subtract 7, we get 5x is greater than or equal to -7. Divide by 5, we get x is greater than or equal to -7/5. That's going to give us our domain, and we have to use interval notation for that. So we will start at -7/5, and everything bigger than that ends at infinity. The other one we have to watch out for is a denominator, because we are not allowed to divide by 0. So anything can be in the numerator, but we can't have 0 in the denominator. So what do we do when we see variables in the denominator? We are going to set the denominator not equal to 0. So I take this problem here, x plus 5 over x minus 10. I take just the denominator, x minus 10, set it not equal to 0, and that tells me that x is not allowed to equal 10. Well, on a number line, if I make my entire number line and the only number that I am not allowed to equal is 10, so I put an open circle there, and then I go this way, and I go that way. This gives me 2 intervals. The first interval goes from -infinity up to 10. The second interval goes from 10 to infinity. So in interval notation, this would go from -infinity to 10, skip over 10, start back up, and go to infinity. This one looks really similar to that, except it also has that radical. So what I'm going to do is I'm going to set the denominator not equal to 0. When I solve this equation, I'm going to square both sides. So I get x minus 10 cannot equal 0. Add 10 to both sides. I still get x cannot equal 10. Great. Then I still have the radical. Well, by the radical, I have to take the radicand, set it greater than or equal to 0. Well, the radicand is x minus 10. So I say x minus 10 is greater than or equal to 0, which gives me x is greater than or equal to 10. Then I have to put these two ideas together. This one is telling me x has to be greater than or equal to 10, but this is telling me x cannot equal 10. When I put those two ideas together, that tells me that x can just be greater than 10. It can't be equal to, and it can't be smaller than. It can only be greater than 10. So that's going to give me a domain in this case. X is greater than 10. It will go from 10 to infinity. When we get to logarithms later, the way that we're going to deal with domain for logarithms, again, this is just later, only positivity allowed there. So we are going to set the argument greater than 0. Well, the argument of a logarithm is the stuff inside the log. That's this stuff right here. So I would just take x minus 4, set it greater than 0, which would give me x is greater than 4. And in interval notation, that's an open parenthesis at 4 and going to infinity. Domain is not as complicated as you might think that it is. You just have to follow these guidelines, and then if it doesn't have one of these things, then its domain is going to be all real numbers. So if I gave you another example and I said, find the domain for y equals 6x squared minus 37x plus 8. Well, do I have any even index radicals with variables? Nope. Do I have any denominators with variables? Nope. Do I have any logarithms with variables? Nope. So if it doesn't have any of those three things, the domain is automatically negative infinity to infinity. So this one is real easy to answer. The domain here would be negative infinity to infinity. So just watch out for those really two things, and you should be perfectly fine.